Hey guys, welcome to the podcast. Very excited to have Nolan Day and Quentin Anthony from Cerebras and Eleuther, respectively. Last week, we released a set of models called Cerebras GPT, and I really wanted to meet some of the important people that helped to make this happen and to go behind the scenes of what it was like to build and train this model. So maybe we'll start off with some introductions. Nolan, maybe just a bit of background on yourself, how you ended up in AI, and why are you working on large language models?
Sure. I'm a research scientist at Cerebras. The way I kind of got into AI during my undergrad, I was working at Apple, as an intern, and they just came out with Face ID. And I was like, wow, that's so cool. Like it would be so interesting if I could be on a team that's sort of like releasing that kind of cutting edge stuff. So I met with someone from that team and I was like, how do I get on your team? And he's like, we're all PhDs. So then I was like, okay, I need to go to grad school. And then I tried an internship after that was machine learning research, and I just loved it so much. I did a master's, and now I'm with Cerebras.
Awesome. Quentin?
I'm with EleutherAI, so we're like an open institute. I originally did physics research in optics in my undergrad, and then this was like 2018, and distributed deep learning started to kind of take off. So I took a class in that and really loved it. So I swapped over for PhD, and I'm a PhD student now at Ohio State studying distributed deep learning. So
wow,
Cerebras is, yeah. So Cerebras is, high on my interest list, I guess.
Awesome. Could you tell folks a little bit about Eleuther? It's an organization that seems to be very influential in open research for AI. How did this organization come about? How are you guys, I guess, funded, given that it's pretty expensive to work on this kind of stuff? And what are your goals?
So Eleuther is a nonprofit research lab, and our focus is maybe let me bring it back. So we started, or others started before me, with GPTJ and GPT Neo. So when GPT-3 came out, there were a lot of people saying, okay, well, let's just make those sort of models, but open, and sort of give OpenAI a run for their money, and then also be able to release everything in the wild. So not only do people sort of do we want to release the model and a paper on it, but we also want all of the code used to train the model to be open. We want even like the development discussions to go online so people can see like how it's made and what challenges people face. And then at the same time, when GPT-3 was released, there's also sort of this landscape where only large organizations with both the compute required to train a large foundation model, as well as the expensive expertise required to train those, were able to sort of direct AI research. And I think we want to sort of democratize that to as many people as possible. We want open data, open models, open code. And then we also want to be able to study sort of the capabilities of those and the interpretability, those sort of research questions that are important, but usually secondary to profit at large organizations. We want to sort of fill in those gaps and ensure that everyone can take a look at what's going on.
It almost sounds like Eleuther is doing what the original OpenAI charter was saying it would do.
Yeah,
for sure. So we get asked a lot, like, are you guys going to pull an OpenAI? It's not the plan.
Is it funded through sponsorships or grants, or how does that work?
It's sort of a mix of things. So like, for example, when we trained like the 20B GPT NeoX model, we sort of CoreWeave footed the bill for the compute, and then they put it up on like their inference platform. So it's sort of I help you, you help me sort of thing in the past. And then now we have other organizations like Stability, who also provide us compute. And then in return, we train good models that are open and that they can make use of.
I see. That's very cool. All right. So the main topic, I guess, we're talking about is Cerebras GPT, which is a family of language models that Cerebras developed and trained on its Andromeda supercomputer. Nolan, could you give us the background on how this project came about? What was the goal of doing this? And maybe what makes these models special versus all the other GPT models out there?
Sure. Yeah. I think when at the inception of the project, we kind of looked at the open source landscape and also the LLM landscape. And the chinchilla paper came out and sort of, I think, changed what the state of the art was in terms of training efficiency in the community. But there was no open source reproductions using the chinchilla setup. And at the same time, we wanted to be able to prove to ourselves and our customers that we're able to train large language models and demonstrate the scalability of our hardware. So we thought, this is perfect. We can. So Cerebras GPT is a family of models from 111 million up to 13 billion, and they're all trained with the chinchilla compute optimal setup. And we use the Pile dataset for that. So that way it could be as reproducible as possible. And then as part of that, we also trained another 5 models from 111 to 2.7 using the maximal update parameterization. So that's like another, I think, very important paper that came out, but hasn't really gotten a lot of adoption. So we wanted to share all these things with the community and sort of do this to further research.
When Chinchilla came out, the paper from DeepMind that basically said, if you want to do a training compute optimal, you should use about 20 data tokens per model parameter. It was so influential. And I just assumed that because the paper is out, that anyone can do this. But you like the research teams at Cerebras made this point that just because there's a paper doesn't mean it's easy to reproduce. Like, what's the obstacle between just having the Chinchilla paper, which is a very detailed paper, and for someone in the wild to like reproduce that work or apply that work?
Well, I think there's a few obstacles, right? Like one of them, maybe the biggest one is there's very few players that are willing to do this in an open way, right? Like I think Eleuther is like one of the very few, and it's very admirable, right? But that's definitely a big reason. Another reason is not only are there few players in terms of like incentive structures, but also how do you actually run these large models on hardware, right? It gets like very complicated, I think, to distribute across many GPUs and things like that. I mean, Quentin here is doing a whole PhD in that field specifically, right? So I'm sure he intimately knows this. So yeah, I think those are the two biggest bottlenecks for the community to get the state of the art all the time. Is like, what are the incentive structures for big organizations to actually provide these things, right?
And I guess the data sets are also a huge one because they famously Chinchilla used 1.4 trillion tokens. And that's a very like arduous, I'm sure, like data gathering process from many, many public and probably some internal Google data sets. And like it's pretty hard for someone to do that on their own. And I think that's why Eleuther's contribution here is so massive. They produced this data set called Pile, which is what we used at Cerebras to train the GPT models. Quentin, like, could you tell us a little bit about Pile? Like, what was that effort like to create that data set? What was what existed before? And I guess like what makes Pile different than the other commonly cited large data sets that are public?
Mm-hmm. I didn't directly work on the Pile, so I want to point that out and not pretend. But from what I understand about the Pile and from being a user, is that it has sort of two big reasons that it took off. And the first is that it's open. So it's really expensive to create a large data set. So typically only big companies make such data sets. They already existed, similar data sets before, but they weren't released to the open. Other people couldn't reproduce results and or even train their models on it because you don't really become a big company by playing nice. Okay, so that was the first thing. So the Pile was sort of like an ImageNet data set where everyone said, okay, we can all use this language data set and we know what the expected result should be. So we have this fixed point and we can tune another knob. We can test, okay, how does changing the architecture change the downstream performance or whatever else? So that's a big one. And then besides being open, the mixture of common crawl and then high quality diverse data sets. So the Pile is composed of a bunch of different types of data. It's composed of books and a lot of academic papers and things like that. And that mix tends to make the model a good generalist model in terms of language. And so those two things together sort of made the Pile take off. as sort of the de facto standard for open language models, at least.
I see. So if I just trained on Common Crawl, like what would you say is the issue versus if I were to use Pile?
So there's a paper on that. I think it's called like if you have 1 million GPU hours, what model should you train? I would recommend people interested in that to take a look. Just from my understanding is that it's not Common Crawl doesn't compose of enough diverse data sets for the model to be able to like generate like text from a book or something like that. And you need that mix in order for your model to do well in inference, so that when a user comes along and asks for it to write like a book excerpt or something like that, then the model won't just freeze or give garbage output.
Gotcha. Do you have any sense of like how long it took to make Pi or how many people were involved?
A lot of people. I don't know about how long. I know that like for Pile v2 that Carper and Eleuther are working on right now, it's taken a long time. It takes a long time to sort of first even identify like what to include, what proportions of each data set to include, and then you have to go out and actually wrangle the data. You do a lot of cleaning, and then from there you just sort of like narrowly clean it, get it all in the same format, that sort of thing. It takes time. I know that.
Okay, cool. Great. So Quentin, maybe we can Nolan, maybe we can like dig a little bit deeper into Cerebras GPT. The training philosophy here is kind of following the chinchilla direction, which is to be training compute optimal. What does that specifically mean? And why did Cerebras take this angle versus maybe the current trend, which is to train to be more inference optimal and to really apply more tokens than like 20 parameters or 20 tokens per parameter?
Yeah, that's a good question. So yeah, first, when Chinchilla says compute optimal, what they mean is training compute optimal. So like, given a training flop budget, what's the best model you can get for that budget, right? Their recommendation is you should train for 20 tokens per parameter, right? Before that, the philosophy was more like the GPT-3 style philosophy, where you just, no matter what your model size is, you just train it for 300 billion tokens. And the only dimension you scale is essentially the model size, right? So we saw these huge model sizes, then we switched to 20 tokens per parameter. And then recently, the Llama work came out, and their largest model is actually just a chinchilla reproduction. Like their 65 billion model, it's 20 tokens per parameter. But their smaller models have gained a lot of traction, as I'm sure you guys have seen on Hacker News and stuff, right? So for example, their 6.7 billion model, it's just the back of the envelope. It's like 1 trillion divided by 6.7. So it's like 149 tokens per parameter, which is, above the chinchilla optimal point. In our Cerebras GPT work, we kind of show that the farther you go away from 20 tokens per parameter, the more efficiency you're giving up. And we sort of characterize how that efficiency drop off happens. And we're actually able to do that both by sort of pulling out data from the chinchilla paper, as well as using all of the Eleuther Pythia models to make direct comparisons to ours, because we have a family of models that are 20 tokens per parameter, and Pythia followed the philosophy of 300 billion tokens for all model sizes. So that allows us to sort of compare, because Pythia essentially sweeps tokens per parameter values, right? And so, yeah, we're able to derive sort of like a degradation function relative to the most training flop optimal power law, so that you can sort of figure out how much you're giving up. But it's a very incomplete discussion to only talk about training flop efficiency, right? And that's exactly why Llama gained so much traction. Their smallest model is more exploiting the inference efficiency side of things. So, like, what's the best model we can train to be like inexpensive at inference, and also the best is just infinite tokens per parameter, right? As much as you're willing to spend. But I think, like in the paper, we have a discussion that there's really two objectives, and you have to actually balance both of them, right? If you wanted to look at the total cost, let's say you use a metric like like amount of CO2 emitted or something like that, right? You have to add up both all the CO2 that gets emitted during training, and then you have to estimate how many inferences am I expecting this model to do, and then what's the CO2 of those inferences going to be? So, for example, like to contrast with the Pythia models, we found that roughly, if you have more than 200 billion inference tokens that you're going to process, then it's better to do to train the Pythia models. That would have been like more CO2 efficient or more like just total flop efficient. But if your models are going to consume less than, or like inference on less than 200 billion tokens, then actually you should go more with like a chinchilla route. So, I think the field should kind of broaden the discussion into this direction of like, let's actually talk about the total cost, right? And it also matters who's footing the bills for this total cost, right? If you're like Meta and you make Llama, you're not actually paying the inference cost of the whole community, right? You're only paying the inference cost of what Meta is going to deploy in-house. So yeah, I think there's a lot of complexity and stuff to talking about this. I don't know if you have any thoughts about it, Quentin.
I think there's a lot of like misconception in the community about chinchilla. I definitely agree with everything you said, but like just as a statement, like chinchilla seeks to answer the question: you have a given compute budget, that is like GPUs over time, so GPU hours. What is the best size of the data set and the number of parameters you should use to get the lowest training loss, beyond which you get diminishing returns? So like a better practical, maybe creating inference-optimal models is to first like decide what is the largest model that you can scale up on your hardware, and then just train it on as much data as you can tolerate. Kind of basically what Llama did. And I think as people understand these scaling laws better, like thanks to studies like what you guys just did, then we'll be able to we'll keep getting closer to what is the actual number of tokens to get inference optimal models.
I think it's a very interesting topic, and it's got so many dimensions. When chinchilla kind of has to be judged in relation to the I guess environment it was released in early 2022. It was this massive industry-wide chase for larger parameter size models. GPT-3 at 175, and then Microsoft NVIDIA was doing things at like 500 billion parameters. It's like all of a sudden it's just like everyone is just going gangbusters on making gigantic models, which is of course a nightmare for distributed parallel computing. But I think chinchilla was really bringing a proper perspective of, there's a far better way to optimize for your end result than just this kind of undirected race to the upper right in parameter count. And I think that's why it was such a important just turning point in reframing the problem. And it is, I think, the most useful construct to view if you are the primary big person or organization bearing the cost of training that portion. Llama is a very interesting way. It's almost asking from the perspective of someone running maybe a local system, what kind of model would I want? And if you frame it that way, you're kind of decoupling the cost of the organization bearing the training and the organization bearing the cost of inference. And if you're just and I think a lot of people online are this latter group, like they don't care the cost of training because that is not something that affects them in any way. That just comes like as an airdrop from large research organizations. But they just want the highest accuracy models they can run locally or maybe on a very tiny kind of cloud instance, in which case they should, by rational self-interest, pick the highest accuracy model and the lowest memory count for the lowest memory. So I think that's why Llama, Alpaca, this line of work is so interesting for people who are like tinkerers and builders on Hugging Face, like solo or small company projects. Whereas if you're a large organization with hundreds of GPUs and a fixed budget, fixed time frame, and you expect, and that basically gives you a constant number up front for how much you train, then you really have to think about it through the chinchilla lens. So it's like this because AI is like has two cost components, training and inference, and now these two are kind of like different groups of people applying them in different ways. Kind of the laws have different relevance for these two different groups. And I guess from Cerebras' side, because we serve primarily practitioners of training and large scale training, like chinchilla is kind of the more interesting, at least first order law for us.
For sure, and there's definitely a need for a want from people and like hackers and small companies to have these really small models like Pythia and Cerebras GPT. Like we're seeing a ton of adoption. People just want something to fine tune and just have it like generate books or something or poems or something small like that, and they want to do it on their own laptop and they want to do it at home and not have to worry about licensing and a lot of other kind of stuff. So I'm super excited about all these new small models.
It is.
I think the licensing aspect is also important to kind of note, right? Because the meta like OPT and Llama models, they're really good models, but they're non-commercial licenses, right? So you can actually do everything that you might want to do. But with the Cerebras GPT or Pythia models, like if you start a startup and make money off of it, the money's yours. So and you can make any extension you want. So I think the community, like it's also good for the community to have models that are completely permissible.
For sure. And on like fully permissible, Apache 2.0 is pretty standard. I think like Pythia, Cerebras GPT, NeoX, all those are under that umbrella, and that's kind of why they're pretty popular and talked about. We talked about Pythia a lot, but it's been in this kind of I guess trial state, and the Pythia paper just released this week. Quentin, maybe just the background. We talked about it a lot. What is the philosophy behind the Pythia range of models? I think you guys talk a lot about interpretability. I'm curious, how does having a fixed parameter count across the model sizes help with interpretability?
Fixed parameter count or fixed token count?
Fixed token count. Yeah.
Yeah. So Pythia from the ground up was designed to be something for interpretability research. So every single model is like consistently designed so that you may have more parameters, and by the parameters go from about 70 million to about 12 billion parameters. And between those, we train them all on the same order, on the same data set for the same number of tokens. And we also have intermediate checkpoints so that you can look over time and over just the architecture of the model, over depth. There's a lot of different ways that you can look how this model is grokking, is learning on the data. We can take a look at properties like memorization. So we can see, okay, well, we know exactly when every single model saw this sample from the data. How do they all, how does their memorization behavior evolve over time? That sort of thing. There's a lot of interpretability questions that you can answer when the data, the model, everything is both consistent and open. And that's what we're really excited about. And then we also get the added benefit of we can release these models in the open. And then since the smaller models are overtrained, quote unquote, they're a bit more performant on downstream tasks. So we've seen a lot of different people take the small models and then fine tune them to some small task, like I mentioned previously. But yeah, the overarching point of Pythia is interpretability research.
I kind of understand intuitively what interpretability means for like maybe like image models, like you want to see how the model sees things. But what does interpretability in the context of LLMs mean?
So an example would be like the memorization that I mentioned. So you want to say like how is this sample stored over time? You want to take a poke around inside the actual parameters themselves, see what they store, things like that. The sort of questions on how the model dynamics change over time and within the architecture.
With the memorization, this is kind of a side question, but does the neural net have explicit memorization of just like raw facts, like dates of things and object names? Is that like stored how is it represented? Like when you think about interpretability, like how can I ask a model, does this thing know that World War II ended in 1945? Like how would you interrogate that?
A good way to think of it is like sentence completion. So like say if inside the data set, it says like John Doe was born in the United States and he's 36 years old or something like that. If you were to prompt the model and say John Doe was, memorization would be the model just completely like completes that sentence based on the data. It just regurgitates what it's already seen. And when you have you could have privacy concerns from that. Sometimes you do actually want the model to memorize. If it's like factual data, you want the model to know what the capital of the United States is, for example. And understanding memorization or something like that requires all of this. You need to know exactly what data has been seen, when it was seen, and then you also want to look across model scale to see how that changes things.
Got it. And when it remembers a thing like the US Capitol, is it still a probabilistic thing, or at some point it's almost like a deterministic thing?
Open question, I would say. It's if the model has already seen the end of that sentence that you're trying to get it to complete, then it's more likely that the model will just regurgitate the end of that sentence because it knows that it can reduce the loss by doing that.
But if there were, I don't know, conflicting answers to the same sentence.
So open research question. Hopefully someone will answer it with Pythia.
That's very exciting. That's very exciting. I feel like we did some ImageNet, convolution nets came out early 2010s. We're all excited, but everyone's like, we don't know how these things work. And then we did some interpretability work, and now it's a lot better. Feels like we're crossing that threshold now for language models, thanks to stuff like Pythia.
For sure. That's the hope.
Great. Let's talk about the infrastructure needed to train these large language models, because that's like an interest area for Cerebras and your PhD work. What was it like training on? Obviously, de facto infrastructure today is GPUs, and there are all these techniques for, I guess, to set up the problem. When models were small, they would fit on one GPU, and it was basically an AI research problem, not anything else on top. But when models got very large, billions and then tens of billions and hundreds of billions of parameters, it was completely impossible to fit them in the memory of a single GPU, which is roughly tens of gigabytes. And then an entire line of work was created to basically break down or cut the model into bite-sized pieces that would then fit onto each processor. After you've done this, of course, the thing is no longer one whole piece, and you have all the communication that has to happen to coordinate still has to happen. So that's the intricate work of turning AI training into a distributed computing problem. And that itself is the thing to understand is that is entirely a separate technical discipline on top of just AI research at the core level. So now it's like two layers of problems, and which is why so few people or organizations can do it competently at the highest scales. At Eleuther, you guys have done quite an admirable job doing this, especially being a pretty independent group and pretty lean group. What was the techniques? There are many libraries and recipes, I guess. What are some of the challenges today in kind of wrangling and distributed training on cloud infrastructure?
There's a lot. Let me think how to start here. So I think the most glaring one is communication overhead. So once you start to train an out-of-core model, most people, in this community at least, for language models, use 3D parallelism. So they're using data parallelism, which is just this established technique. It doesn't even have to have an out-of-core model. You have one replica of the model on each GPU, and then after each forward-backward pass, they all synchronize the gradients. And that's pretty low communication overhead. It's kind of sort of becoming a solved problem on high bandwidth HPC systems and such. But now we have these two other dimensions of parallelism, and one would be pipeline parallelism. And so you have different pipeline stages. You split each pipeline stage is composed of a couple layers, and then you pipeline them over micro batches. So you split your mini batch into micro batches. And then there's tensor parallelism, where you split the matrix multiplication itself across GPUs. So now you have this 3D mesh, and each one of those requires a different amount of communication, but they're all non-trivial. For example, if you try to bring tensor parallelism outside of a single node, you'll get killed by communication overhead. So there's this balancing act of where do you place how many pipeline stages you have, where do you place them, how many tensor parallel units compose each pipeline stage. Effectively, all of your time in communication is wasted, right? Because it doesn't lead to any updates in parameters. So communication overhead is the biggest one. It's the only way like to practically get good performance out of your model is if you're used to tinkering on supercomputers, which not a lot of people have experience with. So that's the first overhead problem. Another one is just cloud systems tend to be kind of unstable compared to HPC systems, and you get a lot of training errors. So like sometimes just hardware failures happen. Sometimes there's some bug in the code, and you have $1 million worth of hardware sitting idle until you fix it, right? So checkpointing your model, you have to checkpoint all the time. Your checkpoints have to be efficient. It's hard to checkpoint when the model is split up all over the place. So that takes a while to get everything synchronized, and then you save the checkpoint. I think, and those two together has sort of created this paradigm of there's like babysitters now for models. Whenever you start a model training, I'm sure you guys know that you have like someone around the clock in every time zone of the world that is awake and watching to make sure that there's not any red output on the screen. But all of that together, I would say that like DL overall has kind of become an HPC problem. And until we sort of apply HPC techniques of distributed checkpointing and communication optimizations, it's going to continue to be a pain point for a lot of people. And when you have a lot of DL hobbyists that don't know anything about HPC, trying to train a model, there's a lot of pain. So that's still sort of an area to be fixed. Cerebras fixes a I'm sorry?
Yes, yeah, we'll get to that for sure. You said that the cloud infrastructure is a lot unstable than HPC. I guess what I was thinking that a cloud GPU cluster today would be HPC grade. Is that not the case? Like, what makes infrastructure HPC grade versus just cloud grade?
It depends on a couple things. So, first off, it depends on the cloud system. But some cloud systems have a lot of usage. So like a company providing a cloud service might be more incentivized to use hardware longer. They might be more incentivized to have more demands on the hardware. Like in a lot of cases, people have more sort of ability to run the hardware harder than on like an HPC system where they're all run by like DOE people who put really strict boundaries on what you can and can't run. And they also they're done by academics, and not as many academics. Let's see. Yeah, it all depends on your provider, but just in my experience, cloud systems tend to be a bit more unstable.
I see. And we should just, I guess, clarify, HPC is high performance computing. It's kind of the infrastructure that standard in supercomputer installations.
Yeah.
Okay, cool. I guess one last question before we switch to Nolan and talk about the Cerebras approach is I've seen that there are a lot of libraries now that try to take away the complexity of doing this 3D parallelism work. There's a library from Microsoft with DeepSpeed, and there's a library from NVIDIA. From reading the web pages, it seems like if you just include the library and then launch the run, all this magic will happen. I guess I haven't done it myself. Like how close is it, or is there still quite a ton of work even if you use these libraries?
It's still a ton of work. Like all of the optimizations that I mentioned, where you have to decide where to place everything and like how parallel you have to decide yourself. DeepSpeed and Megatron DeepSpeed, which is what we trained on a Megatron DeepSpeed based library called GPT NeoX, and it'll do a lot of the work if you're running on an NVIDIA GPU system. It'll get things running, but whether you get things running well is up to you in large part.
Okay.
Like it's not uncommon to see like a 50% improvement overhead once you like spend the time to optimize how your model is distributed and how your distributed training is running. And that difference is all just coming from, black magic and people who have been doing it before.
All right, black magic. Nolan, maybe this is a great way to kind of contrast how your experience is. This is like Quentin's given a great overview of like what it's like to train on GPU clusters, state of the art today. And of course, the whole point of Cerebras is to accelerate AI training and to simplify it to a great degree. What's the hardware architectural difference between Cerebras systems fundamentally versus GPU clusters, and how does that translate into a programming model difference?
Yeah, so maybe I'll start at the highest level. Like Quentin mentioned that you have like data, model, tensor, and maybe pipeline parallelism. With the Cerebras systems, you only need data parallelism, regardless of like for any model size that you would ever want to train. You could just always do it with pure data parallelism, and it just makes it like much more simple to actually like manage these runs and configure them. And it also makes it more simple if you wanted to scale up the training speed. You just buy more boxes essentially, and you're going to get a linear speed up. So if you double your investment in the number of boxes you're running on, you're going to get double the speed. The way we kind of achieve that is the Cerebras actual chip. We call it like the wafer scale engine. So it's the world's largest computer chip. It's basically the largest like square that you could cut out of a silicon wafer, and we just make that all one chip. So it's like 850,000 cores. It has 40 gigabytes of on-chip SRAM and 20 petabytes per second of memory bandwidth on chip. So super fast memory on chip, like that 40 gigabytes of SRAM.
40 gigs of SRAM versus like a typical A100, which is 40 gigabytes of DRAM.
Yeah. So the memory on our chip is much faster, right? And we came up with a sort of an execution model called weight streaming, which can leverage this to train super large models. So the way that weight streaming works is we have this like huge wafer scale engine, and it's hooked up to a bunch of CPU servers that are external to it, right? On the first, like let's say you wanted to process like one mini batch. So the first step would be you stream in all of the input token data for that mini batch onto the wafer, and then you stream in all of the weights for the first layer. So now all of the memory on the wafer has both the input activations to the network and the first layer's weights. Then on chip, you compute all your map mols. So now you have the result of all those map mols as the activations going into the next layer. Then the next step would be to stream in the weights of the second layer into the chip. So the data, like the activations, they stay on the chip, and the only thing you're streaming is the weights. So that's why we call it weight streaming. Because we sort of have that model, you only really need to fit one layer of weights at a time, along with their associated like input activations. And so with this model, it allows us to just fit like very vast parameter counts on single chips. And because we can fit such large models on single chips, this allows us to basically always do linear data parallel scaling. Yeah.
So I guess one key difference here is the reason why you have to do the work division on GPUs is fundamentally because you run out of memory. And you're saying that you don't run out of memory on Cerebras because your memory effectively is decoupled from compute and is this external external set of memory that has nothing to do with the chip itself.
That's right. So if you wanted to buy like a multi-box solution from Cerebras, then it's all going to be coordinated by this technology called SwarmX. And as part of that, we have these essentially just like CPU servers called MemoryX nodes. And the largest model that you could train is only limited by the memory inside those MemoryX CPU nodes. So for example, we have our Andromeda cluster right now. I think the memory that the MemoryX nodes are provisioned right now, we could train up to like a 500 billion parameter model. But it's very easy to just upgrade those MemoryX nodes. So if you ever wanted to train larger, all you have to do is just buy more RAM.
500 billion parameter model on like how many systems?
Like one box. You could train it on one box. It just, it might be slow.
One box is one chip.
Yeah, one box is one wafer scale chip. Yeah.
Okay. Whereas 500 billion parameter model on GPUs, like, I don't know, Quentin, how many typically would, how many GPUs would you source if you were wanting to train on that?
Oh, sheesh. I don't know. A lot.
Roughly.
I don't want to do the math. Hundreds.
I think the Megatron Turing work, right? Like that was on like I think 4,000 GPUs or something like insane like that. So
sounds fair. Yeah.
Yeah.
And even then, the waste it's a waste of a ton of time in communication for any of those. Like the closest thing that GPU programming has to something like weight streaming would be like CPU offload. So like if you try to use like 0.3 and then offload to the CPU, you can do it, but it takes a lot more optimization than even what people are already doing for like zero. And then they also usually get pretty poor performance. So there's not really any analog to the like infinite memory paradigm of Cerebras, I'd say.
I'm going to be the internal skeptic. You're saying you're just streaming these layers one layer at a time, but the memory is external. If given that it takes, I assume ginormous memory bandwidth to feed a whole wafer of chip, doesn't it? I guess wouldn't you be? I guess can you have the memory external and still be fast enough to feed the whole chip?
Yeah, I think the short answer is yes. Yeah, you're always going to get bottlenecks somewhere. So I think the I/O of stuff going into the chip and out of the chip is like 1.2 terabytes per second, if I remember correctly. 1.2 terabits per second. So at a certain size, that might become one of the bottlenecks. But still, it's fast enough that you can get good utilization out of the silicon and train fast.
Okay. I mean, Quentin, how does this sound to you as like someone who's used to the GPU model? Like, does this conceptually make sense, or do you think what are your kind of maybe questions or thoughts of what limitations there might be?
Yeah, well, first off, I assume you overlap data movement, right, with computation. Is that correct? Because
of course.
Yeah. So what do you overlap weight streaming with? Maybe computing the activations?
Yeah, basically like anytime the I/O like would be idle, we're just gonna stream in the next thing, or like as soon as it's possible to stream in that next thing, we're always doing that.
Okay. Yeah. My main concern would be like, it seems unlikely that you could be like an HBM, like a high bandwidth memory on chip GPU with something that's external, and then something that's modular enough that you can just add to like memory X. But if you were to overlap it, and that overlapping is done like not by the user but by the underlying system, then I can't see any reason why that wouldn't work and why that would be a lot easier to do. Like a big problem that is out there is that like GPUs are great if you tune them. Like if you hire a team that knows how to tune them from the ground up, that you write your own kernels and you do all of this performance optimization before you can even think of actually starting a training run. Whereas if something is done automatically for me, all of the overlap between data movement and computation, like talking about on two, is done for me, then that's really attractive.
Yeah, we have a whole stack to just handle everything. So someone like me, it's sort of like I get to operate at such a high level of abstraction. Like I don't need to worry about any of these problems. There's just the stack will just sort of handle everything. So yeah, it's really nice because I guess I don't need to be a distributed systems expert.
And another concern that people would have would be like, okay, I have this software stack. The entire like software landscape right now is kind of built off GPUs, right? It's built around NVIDIA GPUs specifically, and people don't want to become like have to become a Cerebras expert in your own software in your own system in order to hop on your system. So, like, how do you get around that?
Yeah, I think first of all, it's kind of insane that NVIDIA has been able to kind of essentially keep a monopoly on like AI training hardware, right? And I think for us to sort of break that monopoly a little bit, we have to be generalizable enough. So that comes down to the like writing kernels that are going to be generalizable, that whatever common workloads that are out there, we can easily run those. And then the second piece, like we also have an offering similar to CUDA. We have something called CS Lang. So it's a language that you can program kernels for our hardware. So if there's some very specific application, or perhaps you have a proprietary algorithm that you don't want to share, and so you need to implement it yourself, then we also have that covered. But I think in order to have a chance at disrupting NVIDIA's monopoly, like we have to have like some big value proposition. And I think today the Cerebras GPT work shows that just the fact that you don't need to deal with the 4 levels of parallelism is already a huge selling feature, right? Yeah, and there's more there's one more feature which I think is very underexploited so far, which is that our chip is able to accelerate unstructured sparsity. So in the context of large language models and weight streaming, this, like an example would be you apply like a random sparse mask to your weight matrix, and like it could be fully unstructured, but if that mask is 90% sparse, then the map mall is going to run 10 times faster on our hardware. And so this is I think a very exciting research area too, where in the future our system could get even more efficient and sort of unlock workloads that aren't even possible on GPUs today.
Sparsity is real. Oh, I'm sorry.
Go.
And sparsity is really timely too, because we're seeing that all these models are way over parameterized, and that they're still learning something from feeding more data. So it's probably a good thing to I don't know, fill in with holes, I guess. And then I also wanted to say that, like, putting out with Cerebras GPT, a PyTorch model that can see and touch and everything, really, I think, helps people like understand that Cerebras can give me the same outputs as like a NVIDIA GPU model at the end of the day.
Yeah, it was really nice for us to see the like a very close agreement with the models that are out there, like Pythia, for example, right? Because it shows that like literally you're going to get the same result if you use our hardware or NVIDIA's. Yeah. I think one more thing I forgot to touch on too is that with our stack, like the way you actually like would make your models code base, like you could write it in PyTorch, and you just have to specify that, okay, it's PyTorch with the Cerebras device, and just a few other changes, but you can write in either PyTorch or TensorFlow. So that's like one more thing to sort of lower the barrier of adoption.
So if I have a Megatron DSpeed pipeline and I want to put that on Cerebras, then basically it reduces down to the problem of me defining my model in PyTorch and then just training it.
Pretty much, yeah. Like you'd probably just want to start from scratch, because Megatron, like I've dealt with Megatron too. It's like a very complicated code base. There's like so much extra stuff, right? They have all the like column, parallel, linear layers, and like you probably want to just like make a much more simple model definition and stuff. So yeah,
you can just paste into GPT and just say make it simple and strip out Megatron. It would come out right. Yeah, well, it will work for most Python stuff. While on the topic of hardware, what this is just a kind of side question for both of you. What, I guess, people developing software always has like features or wish lists for what they want to see in next generation hardware, or what's coming next. And Quentin, what would you like want to see either on the hardware or maybe programming model side for next gen stuff?
I would love to see, and it's almost similar to weight streaming, but I would love to see like a good CUDA unified memory for which I can just define my model on on some number of GPUs, and then just treat memory as a black box and aggregate memory specifically as a black box, and just let CUDA or some whatever's under the hood to handle that for me.
So virtualize all the aggregate GPU, all the memory across a number of GPUs across nodes.
Yeah, at least within a node. I think, and I know that exists with CUDA unified memory, but I don't think it's been it hasn't really taken off. It's been around for a while, but I don't think people use it. It's probably, maybe it's not as performant as people hoped, but I would like a good unified memory. Yeah.
Yeah, that would be nice. Nolan, what would you like?
I think, like I mentioned, even today, the CS2 can already accelerate unstructured sparsity, but there hasn't been a paper in the field to really showcase that you can get good efficiency gain for like real state-of-the-art workloads. So like that's one thing that I guess it already exists in hardware, but I think it has like so much potential to really increase our efficiency. And then another thing, just with like I'm really excited to see what future generations of Cerebras hardware like how they just improve on whatever bottlenecks exist in the systems today, because it's a very difficult company to try and start to try and like compete with a giant like NVIDIA, right? So whatever hardware that we have today, we have to sort of you have to guess what will the field need in like 1 to 2 years time, right? And in like think of how much like large language modeling has changed just in the past 6 months, right? So the workloads can shift, and you thought everything would be in a certain precision, and it might change, right? So now we see like the H100s, they have FP8 cores now, for example. So I'm just very excited to see the generation over generation improvements for the CS machines, and see like if we further optimize our architecture and make it similarly optimized to where NVIDIA's is today, then I think we're like already that will just be able to showcase that we have kind of a superior platform that we're developing with.
Very cool. I guess one interesting direction is that once AI algorithms solidify around a certain function, sometimes people put specific acceleration units into the hardware. Like for example, I think the Google TPU v4 paper just was released, and they have a special accelerator just for embeddings. On NVIDIA side, they have a special accelerator for transformer operations. Do you think it makes sense to deploy, like, is it like, obviously when you do that, you're betting that the future, that specific way of execution will still exist at a very large scale. Like, what do you guys think of this direction of taking certain things that's pretty common today and then putting them down into silicon? Like, is that a safe bet right now, or still kind of in the open from a ML research perspective?
I mean, I think this kind of gets at like the question of the hardware lottery, which is you have hardware that exists, and then you're going to develop algorithms to fit the hardware that exists, right? Like all of deep learning was basically developed because Alex Krizhevsky figured out he could use his like dual SLI gaming cards, write some CUDA kernels, and suddenly you can like train on ImageNet and stuff, right? So similarly, like if we move towards transformer cores and everything, then what if a better algorithm comes out? Like there's a potential that there's already so much innovation happening in this field, right? And there are competing architectures that have been proposed, right? Like there's the all MLP architectures, and there's some recurrent architectures as well. So I think it's like pretty risky actually. But this question is probably above my pay grade because I'm not a hardware design guy.
It's exactly your pay grade, because it's a software question. Because if the software moves, then the hardware becomes moot if you've baked it into silicon. Quentin, what do you think?
I think tensor cores were a pretty safe bet. Transformer engine, we'll see. FP8, we'll see. Those sort of things. I think until people get their hands on it, and until we see how the AI landscape moves over the next 2 years or something, then we'll be able to look back. That's a hindsight thing.
For sure. And Nolan was referencing Hardware Lottery. It's a paper by Sarah Hooker, a fantastic paper for anyone interested in intersection of ML research and hardware. A last question, from 2023 has just been wild in terms of like AI research and actually putting it out into production. None of us can keep up with all the deluge of research coming, and there's just so many directions. What are you most excited about for this year in terms of AI research that you think is on the cusp of going from maybe theory and plausible to having the first tangible results to show a breakthrough direction? Mm-hmm. Like things that's happened already, like GANs are making a comeback, and we have this amazing segmentation work from Facebook. Like, what do you think? Maybe besides just better and better and more compact large language models would be really exciting this year. Quentin, maybe you can start.
I got a long list, but maybe the top ones would be like sparse models. I think people are just starting to care about. Um, I think that like video generation is going to be something that we're going to start to see this year. Multimodal models in their parallelism schemes is kind of a new thing, especially like in my field of distributed deep learning that I don't think we've tackled enough yet. Um, like the GPT-4 image input sort of thing. I expect to see a lot more multimodal models coming up. Those would be my short list, though.
Do you think the multimodal models will be like, it seems like there are two approaches to multimodal. There's the ones like GPT-4, where it's like the two models are tightly integrated into one, like it's one like unit from the outside that you interface with. Then there is the kind of loose approach, maybe kind of like the Hugging GPT approach, where it's like you have a collection of loose specialized models and then you query them, and it's more modular. Like, which direction do you think makes more sense?
By the second type of model, are you talking about like adapters? Like, so there's like, you have like a language model and a vision model, and you have like adapters between them, and the two models stay static, but you train the adapters so that they learn to talk to each other.
Yeah, so you have like some kind of arbiter up front that decides like which one to send to.
Mm-hmm. And I'm sorry, what was the question?
Like, do you think that style of like modular style makes more sense, or you have these joint trained models where you have within one big model language and vision and like the GPT-4?
Yeah, I don't think that's something I can authoritatively talk about. I would prefer to have models with adapters, like Magma in the second model type you're talking about, because then it's a lot easier for us to take existing models and plug them in to one another. I would prefer that to be the case, but we'll see. I think maybe this year that question will be answered.
Very exciting. Nolan?
Yeah, I think there's still like so much efficiency on the table. So the progress of a lot of machine learning, or sorry, a lot of deep learning is predictable by power laws, right? And so like they also kind of have a bitter component to them, which is that, like we can only 10x our compute for so long before like we just took all of TSMC's like reservation time, and like you can't 10x past a certain point, right? So the like seeing the RLHF training with InstructGPT and Flan and all those and ChatGPT and whatever, that sort of allowed us to transcend the power laws that we had, because we could make something so much better given the same amount of compute. So I'm really interested to see like what other sort of step changes in this power law scaling can we get. There was a really cool paper sort of motivating this, like one of these directions, from Surya Ganguly's group at Stanford. I forgot what it was called, like maybe like beyond power law scaling data pruning or something. But they're basically arguing that the way we just like set a data order where we say like, okay, this is the pile data set, I'm going to shuffle it, I'll just train in all of it. It's pretty inefficient. Like instead we should have some sort of selection criteria for like, based on where we are, what's actually the best next sample for me to train on, right? And I might be able to make a lot more sample efficient progress if I do things like that. So I'm really hoping to see the community go further in that direction and actually make like tractable things and prove it works on large language modeling. I think sparsity is a big thing, but we already talked about that. And then I'm also pretty interested to see if there are transformer alternatives as well. So yeah, like there's a lot of inertia behind transformers, right? So because there's so few players that even have the budgets to tackle these kinds of things, like even if someone comes out with a new algorithm or something, can it actually, like, are one of the big players going to adopt it and actually try it out at scale? And like, how much sense does that make? Because every time they're going to adopt something, that's months of iteration time to validate it and stuff, right? But I am interested to see if transformers will get supplanted by something as well.
Is there any tantalizing hints of like other approaches that might have advantages?
I mean, I think more naturally, like if you think about the brain, it's maybe like very hand wavy to talk about the brain, right? But like a couple of features in the brain. Like one, you see like sparse weight matrices. Of course, like we kind of abstract everything away into like rate coded networks with modern deep learning, right? But they have a spiking component, but we're not going to tackle that anytime soon, I think. But the other component inside the brain is you have like this recurrence, right? So today we just model everything as sort of feed forward networks, but the brain, there's no direction, or like you can't like pick out layers in the brain, right? Everything is just this like big messy web. And recurrence is a big graph, right? And I think recurrence is like a really important feature that's missing right now. So to me, it seems more natural for us to settle on an architecture that actually has recurrence into it, because that seems like a pretty natural way to build memory into deep learning, right?
Isn't RNNs having a brief resurgence right now? It seems like I'm seeing a bit of chatter that RNNs are being scaled up, actually perform quite admirably compared to transformers.
Yeah, I saw one repo. I can't remember the name of it. That's why I haven't dropped the name. But yeah, I think there's some challenges with recurrent networks, right? You had like the vanishing exploding gradients and all that stuff. But we have some techniques that have been developed to sort of solve some of the stability problems that we see in neural networks. Like the maximal update parameterization is an example, right? So I wonder if someone takes a more modern look at RNNs, if we can't like build that into the architectures we have today.
I could be just making this up, but I want to say the paper's like, or at least the tweet is called like Revenge of RNNs or something like that. But yeah, it's fascinating that the old school approachers are not just dying on their feet. RNNs, convolution nets, and what's the other one? GANs are like, there are still people like prodding them and seeing if they can get to state of the art. It'll be interesting if we just continue along the default path, or some of these retro approaches actually make some comeback this year.
Also, training objectives and stuff too, right? Like we train with a language modeling objective, but I think the model of like GANs with their objective, you sort of have this like iterative self-improvement that's possible. And I think that's a pretty unexplored direction inside of language modeling today. But I kind of feel like that's also an inevitability that that people are going to move towards. Maybe they already have, right? It's too close today to even know. But yeah.
Very cool.
I am excited about the maximal update parameterization work that you guys did. A lot of people are working on integrating that into their pipeline. So for people out of the know, maximal update parameterization, so MUP, is just it's a way so that you can hyperparameter tune a smaller model, and then when you scale up to a larger model, then those hyperparameters are still valid. So you do all your hyperparameter optimization on a really tiny version of the model, maybe on one GPU, or some small amount of memory X on the Cerebras system, and then you save a lot of compute, right? Because before people even start training, they have to spend all this compute finding the optimal hyperparameters, and when you do that at scale, that's really expensive. So I just applaud you guys for training models on that and showing that it's possible beyond the original paper, that is.
Yeah, I was pretty surprised that it hasn't been adopted like widely, at least in the I haven't seen papers that explicitly state that, okay, we use maximal update parameterization like since that paper. So I'm sure that many closed source shops have done that already, but I was glad that we could at least help the community hopefully like adopt it more. Yeah.
It's kind of hard to integrate on GPU systems from my experience, so that might be part of it. Because you have to have, if you're trying to transfer to a really large model, then you have to worry about like transferring parallel models, and that's kind of hard to do.
Yeah, I actually gave an attempt at trying to do it in Megatron, and it was like, it's very complicated. But I think like in our paper, we sort of distill things down a little bit. So hopefully it's simple, like the implementation is simplified no matter what code base that you're looking at. So yeah, I guess stay tuned for the paper, which should be coming out like tomorrow or Monday or something.
Yeah, I think by the time you're listening to this, the paper should be out, and it has some great comparisons on the standard training and the maximum update parameterization. And yeah, it's an exciting line of work. Gentlemen, it's been great chatting with you. I think we went through a lot of ground here. Very excited for the work Eleuther is doing, and of course that we've done at Cerebras. Hopefully, we'll continue to release great research for the year.
All right, thanks all.
All righty, bye.